Now that we know about Ohm's law, we're going to take that V equals IR and apply it to calculating current, missing voltages, maybe missing resistances in series and parallel circuits. Looking first at series circuits. When you have a series circuit or part of a circuit has components that are in series, there is only one path for current flow. So if you put your pen or your finger on the circuit and you start traveling around, you will never hit a point where you have a choice. There's no junctions. There's only one wire. All the loads are attached, I guess, to that wire. There's an in and an out. And that's what a series circuit looks like. There are a few things you should really know, like have memorized to heart about series circuits. When you want to find out your total voltage, E or VT, it is going to be the sum of all the voltage drops at each resistor. So we have three resistors here, R1, R2, R3, and I know that if I want to find VT or the E, we're going to add them together. So they must add up to the total voltage. And as you go through, you have VT at this point, and by the time you get through all the loads, wherever that might be, your voltage will be 0 volts. You've used it all up. Likewise, resistance, the total resistance of a circuit, I'm just going to put little t's in here, I don't know why I didn't before. The total resistance will be the sum of all the resistances that are on that series circuit or branch. R1 plus R2 plus R3 will have to add up to the total resistance. And how do we know what the total resistance relates to the total voltage and the total current? That's just our VT equals IT times RT. So we can use this formula at each resistor, and we can use it for the whole circuit. And you can rearrange this formula to isolate. I is V over R, and R is V over I. This is the only formula we're going to be using, just kind of messing around with it as we go through these circuits. The neat thing about current in a series circuit, it's equal everywhere. So current doesn't change as you go across a resistor and you drop voltage. The current stays the same. So if you figure out IT, you know the current everywhere in that circuit at resistor 1, at resistor 2, and at resistor 3. It just continues to flow. Its value does not change. So let's look at an example. First, you verify that you're looking at a series circuit. You take your finger, you trace around all the components. You should never have a choice of direction. Everything's on the same path. You're just on the rope from start to finish. Okay, so what did we say we knew? Well, these problems, we've got a total voltage. And, you know, we have three resistances, which we know we can add up. And we can use those two pieces of information to solve for the total current. And this is how these problems usually go. Find the total resistance, use that to get the total current, and then figuring out what happens at each location that is important to you. All right, so our RT, total resistance, is just going to be the sum of everything. Oops, apparently I'm adding R3 in before R2. I'm probably going to list them in the right order. So I'm doing 3 plus 10 plus 5 equals 18, but these are kilo ohms. And you'll remember last video we said if you want to do the calculations, use V equals IR, you must be in the base unit. So I need to change kilo ohms back to ohms. I'm going to do that by multiplying by 1,000, and I get 18,000 ohms. So if I want to find the total circuit current, I take the voltage, which is 9, and divide it by the total resistance. And that's going to give me a very small number. That is fine. 0.005 amps. So that's half a milliamp, quite small, but leave it in amps for future calculation. So if my total current is 0.0005 amps, what's I1, I2, and I3, the current across each resistor. Well, remember in series, current always stays the same. So that is going to answer part of the question. The current at R1 and R2 and R3 is going to be the same as the total current. And once we know that, we can use the individual resistances and the circuit current to solve for the voltage drop at each resistor. What do we expect to see? 3 numbers that better add up to 9, or we've done something wrong. So here we go. The voltage drop at resistor 1 is going to be the value of the resistor, which we are going to do in ohms, 3,000 ohms, multiplied by the circuit current, or I1 if you want, they're the same thing. And that's going to give me 1.5 volts. Moving to resistor 2, the voltage drop at resistor 2 is the 10,000 ohms the resistor is, and I'm going to have to put it there, multiplied by the current through that resistor, and that will give me 5 volts. Already I know what I should expect. V3 should be equal to 9 minus 1.5 minus 5. It should be equal to 2.5. You can either use subtraction to find that, or you can check to make sure you're doing everything right by multiplying 5,000 ohms times I3, which is IT, and that gives me 2.5 volts. Okay, total voltage, just to check my answers, make sure, is it equal to 1.5 plus 5 plus 2.5, which is equal to 9? Yep, you did it right. This slide is really just kind of setting up for our next video where we deal with combined circuits, circuits that have both parallel and series components, and that is exactly what I'm seeing when I look at this. You'll totally be able to solve this, no problem. But for now, I just want you to look at it and identify which resistors are in series with each other. And by all means, pause the video, do that, and then resume. So as I look through, I see a parallel branch, right? If I go through, I'm in series, I'm in series, I'm in series, and then I have a choice, right? I'm no longer in series at this junction. My current can split, and we'll deal with parallels right after this. But if I just kind of go to the top, I see I can go through R2, and then I go through R3 directly. I don't have to make a choice. So I can say that R2 and R3 are in series. If I was down at R4, like it's with itself, the current split down here, there was only one resistor, and then the current kind of came back together at this point. Like I said, that's the next slide. So R4 is not in series with anything, but there is one other pair in series, and this is a hard one to visualize, but imagine we took out, like I took out this whole chunk here, just removed it from the circuit. What would I have? I would have R1 and then nothing, and then I would have R5. So even though something happened in this parallel branch at this location, R1 and R5 are also in series with each other. So recognizing that R1 and R5 are in series. Find their combined resistances. Well, you know the rule. If they're in series, you can add them together. And the combined resistance, and I'll call that R23, because they're both in there, is 10 plus 4 equals 14 ohms. And R1 and 5 is 5 plus 8, I'll write this one down, equals, it's not R15, it's R1 and 5, equals 13 ohms. So that's series circuits and series components. Next, we're going to look at simple parallel circuits. And the idea for a parallel circuit is you can go through, and there's a lot of ways to draw parallel circuits, so I always recommend redrawing if it doesn't make sense when you see it. And once we hit point A, which is the same, this is still point A here, we have like 3 different paths. So another way to draw this even would be, and it's going to be ugly, battery, I'm removing some of the cell, and I'm dropping the switch. You know, you could just be like, whoop, whoop, whoop. So that's A, there's R3, R2, and R1, and then we just kind of come back at point B and finish the circuit. Same circuit, different drawing. These pieces of the conductor are just wires, so they're equivalent to what you see I drew above them. Okay, so all parts are between two common points. That's A and B. What happens is you can have multiple paths for current to flow. So current is going to split. You're going to have I1, which is going to go down here, and then you're going to have some amount of current I2, which is going to go down here, and some amount of current I3, which is going to go down the third branch. And these don't necessarily have the same value. Like, it's not going to be like if you had 3 amps at the start, it's not going to be like one's going to go down R1, 1 amp is going to go down R2, and 1 amp is going to go down R3. If they were all the same resistor value, yes, but if the resistances are different, no, that's not how it's going to go. So I total is the sum of the 3 branch currents. Okay. What's interesting in parallel is the voltage drop in each branch is the same. So if I had, say, 120 volts here, and I only had parallel stuff, I'm going to drop 120 volts here, here, and here. So it's like they kind of, the voltage and the current are flip-flopping, right? They're doing exactly the opposite kind of behavior in parallel than they were in series. So be it. The terrible one for parallel circuits is solving for the resistance, because we have what we call a reciprocal. So the idea behind a reciprocal is if you had something like RT and you wanted to know what its reciprocal was, you just put it as a fraction over 1, because that's the same thing. RT over 1 is the same as RT, and you flip it, and it becomes 1 over RT. So with two numbers, if you had 2 over 3, the reciprocal of 2 over 3 would be 3 over 2. So just a bit of lingo that I want to make sure we have. Okay, so the reciprocal of the total resistance is the sum of all the reciprocal resistances. So you cannot just do R1 plus R2 plus R3. You have to do the flip side. I have a couple of cheats to offer up that might make it better for you. Cheat number 1 is golden, but it only works if you have 2 branches. So this circuit that I've written in the orange box is going to look like this, only 2 branches. So this is when you can use cheat number 1 if you have this kind of situation. And we have 25 ohms here and 60 ohms here. So here it is. You multiply the 2 resistances together and divide that answer by the 2 resistances added. So for this situation, RT is going to be 25 times 60 divided by 25 plus 60, which is the same as saying 1500 divided by 85. And if you do that math, you're going to get RT is equal to 17.65 ohms. And this just avoids dealing with those reciprocals. Because cheat number 2, you can use infinite branches. It's not as awesome as cheat number 1, but it still works, because otherwise you're stuck doing 1 over RT equals 1 over 25 plus 1 over 60. And that's fine. You can do 1 divided by 25, figure that out, and you can do 1 divided by 60, figure that out. In fact, I'll do that. Hold on. Here we go. 1 divided by 25 is 0.04. That's not terrible. However, 1 divided by 60 is gross. It is 0.0166 continuing, so I'll just put a few 6s and then change to it, round up to a 7. And that's going to be 1 over RT. This isn't even the total resistance yet, is equal to those 2 numbers added, 0.056667. So in order to find RT, you would have to do 1, sorry, that's a crazy looking RT, 1 divided by 0.056667. And that would give you 17.65 or thereabouts. It's a pain. So if you can find the inverse button on your calculator, it may look like this. It may also look like 1 over x. So being able to locate that and use that button helps, because you can just press that and that will flip it for you, right? That's a reciprocal button. I said inverse button, I meant reciprocal. So if you can find that reciprocal button, that will flip the number for you, and it can even flip the answer. So here, this action is creating 1 over 25. This action is creating 1 over 60. And this last action here, when you hit afterwards or before, however your calculator works, is creating RT from 1 over RT. So mess around with it. Use these numbers. See if you can figure out how to get 17.65 and you're comfortable with it. Otherwise, do the long way. Okay, here we have a very simple parallel circuit. I see that there are 3 branches, so I'm screwed. I am not going to be able to just use that cheat where I multiply the numbers together, then divide by the sum. Oh well, you knew it was going to happen this way. So we want to solve for voltage drops and currents through each resistor. Well, what do you know in parallel? I see that I have a total voltage, which is 240 volts. And by definition, I know that the voltage drop across each resistor, because there's nothing else in this circuit, just this one parallel bank, is going to be the same. So V1 is going to be 240, V2 is going to be 240, and V3 is going to be 240. Excellent. Okay, so knowing that, you could very easily solve the circuit, the current at each resistor very quickly by doing 240 divided by each of these resistances. But I want to do the long way just so we work with those reciprocals. I know that the total circuit resistance is going to be equal to, and I'm doing this to figure out the circuit current, it's going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so 1 divided by 120 is approximately, and I know when I do it this way, I'm going to get some rounding errors too. And then my second are 1 over R2, 0.0222, just trying to keep the same number of decimal places. 1 divided by 360, 0.0028. I add those together. And remember, this is not the total resistance. It's a reciprocal of the total resistance, and I'm going to get 0.03328. I know it should be 0.303 continuing, so I'm already seeing some rounding changing it. And if I rearrange that equation, I'm going to get about 30 ohms. And you'll notice also, when you do the total resistance in a parallel bank, it's always less than individual resistors. Just something to think about. Okay. And now we're going to go back and solve it the easy way for the currents, because I don't know how everything's going to split. I can find the total current by doing 240, the total voltage, divided by the total resistance, and that's going to give me 8 amps. But I don't know how it's going to split up in these branches. But because I know that we have 240 volts in each, that's where I will go back and find my branch current. 240 divided by 120 equals 2 amps here. 240 divided by 45 equals, what do we got there? 5.3, yeah, 5.3 amps in this branch. Notice the lower the resistance, the higher the branch current. And 240 divided by 360 ohms is going to give me 0.7 rounded amps. What do I know? They should add up to that total current. So this is the other way I could have found total current. That would have been a little less painful than finding total resistance, but it's good practice. I'm checking is 2 plus 5.3 plus 0.7, dot in there, equal to what I need it to be, 8 amps. Sure is. Circuit solved. Back to our combined circuit to find out which resistors are in parallel with each other and to find their combined resistances. So we're kind of cheating ahead into combined circuits here, because remember last time we said this piece was in series and we said it was like, could be thought of as a single resistor with a combined resistance of 14 plus 10 plus 4 is 14 ohms. So what's in parallel? R4 is in parallel with, you could say R2 plus R3 in brackets. You could say R2, 3. It's not just in parallel with R2. I guess, yeah, it's in parallel with the two of them. Don't know if I'm making sense there. All right, let's find their combined resistance. We've got 2 branches, so we can use that cheat. So the parallel combined resistance will be 14 times 20 divided by 14 plus 20, which equals 280. Oops, I put a double down. 280 divided by 34, which is equal to about 8.24 ohms. And you can be like, but that's less than 4 ohms. So remember, 4 ohms was combined with that 10 ohms to make 14 ohms of resistance in the top branch of the parallel circuit. Lastly, I want to talk a bit about how shorts and opens are going to affect parallel and series circuits. So an open, of course, is a break in the circuit. If we are in series, what happens when there is an open? So if we're just like happily about to go around, this part here is in series, R1 is in the main series circuit, so I'm happily going around, and then I can't flow. Current can't flow. So there's no voltage, right? You could say the resistance is like infinite. You've got no current, no voltage drops. And you can just say R, it's like resistance is infinite. And that's how it might show up on your multimeter. If you have an open in parallel, you're going along happily through the series resistor, you get here, and this is not a path anymore. What have I done? I've changed the circuit. It now looks like this with only R1 and R2. So suddenly the circuit resistance has gone up or down. Think about it. The resistance will go up, because remember we said in parallel the total parallel resistance would always be less in the 2 branches. Here we have 100 and a 25. R2 is 100, R3 is 25. So I know that the total resistance, the parallel resistance in there, would be less than 25. But now I've created a situation where it's 100 plus 20. If you have an open in parallel, the resistance goes up. If the resistance goes up and the voltage doesn't change, the current must go down. So if you put your multimeter anywhere or your amp clamp anywhere on this in this circuit and measured, you would see current that was too low. And that could be caused by a corroded connection or a full-on open in a parallel branch. When we think about short circuits, we basically say take a component and treat it like it's turned into just a wire, part of the wiring. So here, in the short in the series component, you just ignore it. It's like it doesn't even exist. Okay, so if that is shorted out, what is going to happen to the total resistance? Well, it used to have this 20 ohms from R1 and now it has 0 ohms. So we know that the resistance is going to go down when we short out a component in series, and the current goes up, and that's why you blow those fuses when you have shorts, right? If the current exceeds what the fuse rating is, it's going to blow the fuse. Okay, what about a short in parallel. My current is going around, and I see this kind of nice thing. And how much of my current is going to choose to go down this path with a 100 ohm resistor in it when my other choice is a path with 0 ohms? Absolutely none of it. It's going to be a short in a parallel circuit makes all the current go this way, and it basically does the same thing. It changes it into a series circuit, but a series circuit where you've removed a resistor and the only circuit resistance you have is 20. So resistance goes down and current goes up. No matter where those shorts are in series or in parallel, they lower the circuit resistance and cause a higher current flow.